Howdy, howdy, this is Mr. Potter. What we're going to be talking about today is we're going to be talking about the relative rates of growth of function. In other words, which functions grow faster than other functions, which functions grow slower than other functions. And if this sounds familiar, it's because we did a lot of talking about end function behavior back in chapter 2, where we would talk about how a function behaves as x approaches infinity or as x approaches negative infinity. And we often saw this being a horizontal asymptote for some functions, or that a function would approach 0 or a function would approach infinity for other functions. But what I want to do today is, in that same vein, the idea that we were talking about the limit as x approaches infinity of one particular function to figure out its end behavior. It's either going to be 0 or some constant or infinity depending on the behavior that we expect. I want to compare functions. So I really want to take a look as x approaches infinity to compare two functions, f of x and g of x. And in this act of comparing functions, I'll notice something. That if this limit is equal to 0, then that means that f of x grows slower than g of x. In other words, there's going to be some point where from every point beyond that x, g of x is going to be greater than f of x. And if I end up with infinity, then I'm going to find out that f of x grows faster than g of x. In other words, for some value of x, for every point beyond that x, f of x is going to be greater than g of x. Or I'll find that I get some constant out of this. And if I get a constant, that means that f of x and g of x grow at the same rate. Which means that basically f of x could be thought of as k times some g of x once I get beyond some value of x. There's some dominant term in the function that's going to be just a scalar multiple of the dominant term in the other function. And so I'm going to be looking a lot at these limits of a ratio of two functions as x goes to infinity. And of course, we know that as x goes to infinity, a lot of our functions do go to infinity, but I want to compare them. So I'm expecting that I'm going to end up with an indeterminate form, infinity over infinity, quite often. And so that was the whole reason that we talked about L'Hopital's rule. Of course, the whole idea that we went through this was to talk about how do we deal with these situations when I have a limit of two functions that are of an indeterminate form. Especially in this particular example, I'm going to be dealing with infinities over infinities. So I want to talk about my champion. E to the x is going to be our champion function, because what we're going to notice is that if I take a look at the limit as x approaches infinity of e to the x over any polynomial, let's go ahead and say x to the 10th power. I'm going to notice that this limit is going to tend towards infinity, and I'll go through a demonstration of what's going on here. Obviously, I've got an indeterminate form as x approaches infinity, so I can use L'Hopital's rule. But what's nice about dealing with the exponential function is that as x goes to infinity, e to the x, its derivative is e to the x. Whereas when I take the derivative of a polynomial, it's going to decrease its degree by 1. So I end up with 10x to the 9. It's still going to infinity, and so I'm going to need to take the derivative another time. Now when I take the derivative here, e to the x remains e to the x. But this 10x to the 9th becomes 90x to the 8th. And of course, every time I take this derivative, my polynomial is going to go down a degree, even though this constant is going to get bigger. So my constant is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So I'll actually end up with e to the x over 3,622,800. X to the 0. When I finally take that last derivative, that makes this no longer polynomial, but instead constant. And no matter how large this denominator is, if it's a constant denominator, and my function at top is variable and increasing without bound, this limit is going to tend towards infinity. And one of the things that we're going to discuss a little bit more is that e to the x is actually going to be more dominant than any polynomial that we could come up with a integer or with a positive exponent. So that's something that's going to be our champion here. E to the x is going to be one of our fastest growing functions. And of course, exponential growth is one of the fastest rates of growth that we can come across in a mathematical situation. Now, what else is going to happen is if I've got a challenger, then I'm going to have some type of ultimate underdog, and natural log x fills that bill. Because if I take a look at the limit as x approaches infinity of natural log x over, say, some polynomial like x squared, the act of taking this derivative using the L'Hopital's rule, this is going to give me the limit as x approaches infinity of 1 over x over 2x. And now I end up with a polynomial where basically this contributes to the degree of the other function. So I'm going to have the limit as x approaches infinity of 1 over 2x squared, and that limit's going to go to 0 because of the way I know the end behavior function of reciprocal functions. Now, I did this with x squared, but I could have done this with x to any integer, any positive integer exponent. In fact, I could even look at this for the limit as x approaches infinity of natural log x over something like the square root of x. Because this is x to the 1/2 power. And so the act of taking this limit as x approaches infinity by using L'Hopital's rule, I get 1 over x over x to the, well, it's going to be 1/2 x to the negative 1/2. But remember that this contributes to the degree of the denominator. So this is going to give me the limit as x approaches infinity of 1 over 1/2 x to the 1/2 power. And this still is a bottom-heavy function. The square root of x function is going to grow faster than the constant 1 function. So this limit comes out to 0. And what I'm going to find out is that if I compare x cubed or x squared or x, even if I'm dealing with x to the 1/2, as long as I'm dealing with an n where n is greater than 0, natural log of x is going to grow slower than that function. As a matter of fact, natural log x is one of our slowest functions that still tends towards infinity. Now, so I do have some semblance of order here, and I kind of mentioned briefly these terms. I could set these up as a limit. So let me go ahead and do one quick example. Let's say I want to compare the limit as x approaches infinity of a polynomial of degree 3 over a polynomial of degree 2. Now, I could use L'Hopital's rule, but I could also use the power of algebra, that the limit as x approaches infinity of this reduces to x over 1, which is going to tend towards infinity. And so I see that I do have this semblance of order where as long as the exponent is larger, or the degree of the polynomial is larger, then I'm going to end up with a faster growing polynomial. So looking at this from some grand scheme of things, let me go ahead and add a blank page in here. If I want to compare polynomials like 3x squared plus 2x and 6x squared plus 5, if I wanted to look at the limit as x approaches infinity, even though 6x squared is always going to be bigger than 3x squared, and there is going to be some point where 6x squared is always going to be larger than 3x squared for any value of x. If I take a look at this limit using L'Hopital's rule twice, that's going to give me 6 over 12. Which is just 1/2. This is my constant. And so we say that 3x squared plus 2x and 6x squared plus 5 grow at the same rate. So in the example that I just showed you where I was coming up with this order, this hierarchy of functions, when I talk about x squared, I'm really talking about a polynomial of degree 2. And when I'm talking about x cubed, I'm talking about a polynomial of the degree 3. And I do have this ordering here going all the way down to, as long as n is positive, I'm going to have functions that grow faster than natural log x. So the next thing that I want to talk about is I want to talk about comparing exponentials, because just because we're dealing with exponentials does not mean that they're all going to grow at the same rate. So let's real quickly compare y equals 2 to the x and y equals 3 to the x. So comparing these two functions, if I wanted to look at the limit as x approaches infinity of 2 to the x and 3 to the x, right now I don't have any way of really comparing these two functions. So I could try and take the derivative of them, but because they're not base e, the derivatives are a little bit more complicated than we're usually used to. So I've got the limit as x approaches infinity of 2 to the x times the natural log 2 over 3 to the x times the natural log of 3. And notice that this act of taking the derivative is not really simplifying the functions. In fact, it's adding more coefficients. It's adding more terms. So what I really want to do is, in this situation, L'Hopital is really not going to help me. What I really want to do is I want to take a look at this from an exponential idea. The idea is that when I talk about 2 to the x, this is really e to the x ln2 power. And when I take a look at 3 to the x, I'm looking at this as being x times ln3 as the exponent. And so what I've got here is I've got two functions that have the same base and different exponents. And from what we know about properties of exponents, this should be e to the x ln2 minus x ln3, or e to the x times ln2 minus ln3 as x increases without bound. Now, I'm looking at this term here, and this ln2 minus ln3, this really isn't a positive value. So this is really the limit as x approaches infinity of 1 over e to the x times ln3 minus ln2. This is a positive value now. And so this limit is actually going to tend to 0. And so what we're able to discover is that 2 to the x grows faster than 3 to the x. And in fact, we can say if a is bigger than b, then a to the x will grow faster than b to the x. So that's really something that we can do for pretty much all exponentials. And the argument's going to follow the same logic that we did in this one example. So what happens is that we have this kind of grand taxonomy of functions. To the lower end, we have the natural log of x, and this is going to be less than any of these degrees like x to the 1/2 or x to the 2/3. As long as these functions are gaining in degree, then they're going to be growing at a faster rate of change than the previous functions. And so I'm dealing with polynomials of the degree 2, polynomials of the degree 3. There's going to be some polynomial of degree n, but no matter how big that n is, I can have an exponential that's much bigger than that. I could have x to the 1 billion, and that's still going to be less than 1.0001 to the x. Exponentials will always grow faster than polynomials, even with huge exponents for the polynomial and minuscule positive bases for the exponentials. So here's now I'm dealing with my exponentials. I've got 2 to the x, I've got e to the x, I've got 3 to the x, I've got 4 to the x. And that's just going to keep going in that direction. Of course, this is going to be really my smallest function that actually goes to infinity. Once I start looking at other functions beyond this, functions, now I'm dealing with polynomials that are have a degree less than 0. So now I'm dealing with, say, my x to the negative 1/2, or my x to the negative 1, or my x to the negative 2. So these are functions whose degrees, because they're negative, these functions are actually going to go to 0, which means that my constant functions have to lie in here as well. So in this grand taxonomy of functions, I've got my exponential functions that really are kind of the top of the heap. I've got my polynomial functions where the degree is greater than 0. And then kind of standing alone, I've got the logarithms. And all of my logarithms will actually be at the same rate because I've got the change of base idea for logarithms. So if I wanted to compare, for example, the log base 10 of x with the log base 2 of x. This is really going to be the limit as x approaches infinity of natural log x over natural log 10 divided by natural log x over natural log 2. And this ends up being a constant, just natural log 2 over natural log 10. So because this is a constant, these all kind of have the same rate of growth. And then I've got my constant function. And then I've got my polynomials of degree less than 0. And of course, my constant functions are going to approach a constant value. These degrees which are less than 0 are going to approach y equals 0 as x increases without bound. And all of these, including natural log, as x goes to infinity, my function will also increase without bound. The question, of course, is which one increases faster, which one has more growth over that period of time as I'm going towards infinity. So it's a good idea to try and do some type of comparison with these. We're all still using L'Hopital's rule to evaluate these limits because all of these limits are dealing with what we deal with indeterminate forms, this infinity over infinity that we're used to. So I do thank you for watching. This is Mr. Potter. Have a great day.